Hi everyone, my name is Niels Westhausen and I'm a PhD student in the Communication Acoustics group of Bernd Meyer at the University of Oldenburg in Germany. This is the presentation for the paper tPLCnet, Real-Time Deep Packet Loss Concealment in the Time Domain, using a short temporal context. Digital speech communication is performed with audio packets. The digital audio signal is chopped in smaller pieces and transmitted over a network. Because of a bad network connection, packets can be overly delayed or lost. When this happens, the audio will sound choppy and the listening comfort and the subjective quality is reduced. Additionally, the effort is increased to follow a conversation, or with heavy loss, the speech cannot be understood anymore. To reduce the impact of such missing packets, packet loss concealment algorithms can be employed, which try to conceal the lost packets by trying to predict the missing speech from past information. In recent times, more and more processing steps in virtual communications, like noise suppression or acoustic echo cancellation, have profited from deep learning approaches. The same is tried in this study to build real-time capable deep learning model to conceal the loss of audio packets in voice communication. In the recent past, Microsoft organized a number of challenges to address different processing steps in voice communication, like noise suppression or acoustic echo cancellation. For Interspeech 2022, they organized the first Deep Audio Packet Loss Concealment Challenge. The challenge organizers are providing clean speech data and packet loss traces from real Microsoft Teams calls as training and test data. The packet loss traces are vectors with 1 and zeros, indicating if a 20 milliseconds audio packet is lost or not. Additionally, a first version of a so-called tPLCnet estimator is provided as a metric, which is a deep learning model trained to estimate subjective quality ratings of audio processed by a PLC algorithm. The final evaluation of the PLC challenge is a combination of a crowdsourcing approach where the quality of the enhanced file is rated compared to the clean audio, and the word error rate as calculated by the F0 Cognitive Toolkit. More information on the challenge can be found on the challenge website or the challenge paper. In the following, I will explain our deep PLC approach. Our system is based on a context buffer of n non-overlapping 10 milliseconds frames with 1 frame look ahead. First, it is checked if the current frame x or the look ahead frame x plus 1 is lost. If one of these frames is lost, the tPLC model makes a prediction based on the context buffer. The predicted frame is 20 milliseconds long and is time aligned with x and x plus 1. If no loss is detected, x and x plus 1 are concatenated. The intermediate output frame is unwindowed, which is similar to crossfading and reduces artifacts at the edges of the frame. The 10 millisecond output frame y is predicted by an overlap add procedure and returned to the output and also written back to the context buffer. One advantage of the structure is that it's only run when loss is actually detected. Compared to most speech enhancement models, our tPLCnet is based on a context buffer and is so a sequence to one model, which maps the context buffer to just one output frame. First, the context buffer is processed by a fully connected encoder layer and followed by another fully connected layer to build intermediate embeddings. Next, 2 conf1d layer with kernel size of 4 and 2 are extracting more local information. The last sequence processing steps are 2 bidirectional GRU layer to use the information of the whole sequence. Only the last hidden state is returned. The last hidden state is processed by 2 consecutive fully connected layer and is finally mapped to the 20 milliseconds output frame by a decoder layer. In total, we trained 3 different size configurations: small, medium, and large. Only the 5 middle layers were varied in size, while the encoder, the mapping, and the decoder were kept constant. This was done because the non-sequence processing layers are not contributing as heavily to the overall computational complexity. The size of the context buffer was set to 6, which has shown to be a good trade-off between complexity and predicted speech quality. It should be noted that during training, the predicted output frame is not written back to the context buffer, because this would result in a recursive gradient calculation, which slows down the training by a large factor. But to still imitate some variance in the buffer during training, the 4 most recent frames are sampled from the degraded signal, while the last 2 frames are from the clean signal. This was found to be a good strategy in preliminary experiments. Now let us come to the data and the training procedure. In total, we had 64 hours of clean speech and packet loss traces. During training, a random speech sample and a trace are combined to a training sample. With a 50% chance, the trace is time reversed to create additional variance. The tPLCnet was trained on batches of 16 samples with a length of 8 seconds. The known test data provided by the challenge organizers contained 2.7 hours of speech and trace data. The data can be classified in 3 categories: low loss with a burst loss length up to 120 milliseconds, medium loss with a burst loss from 120 to 320 milliseconds, and high loss with a maximum burst loss from 320 to 1000 milliseconds. Now let us go to some audio samples. First, let me play the corrupted audio sample.
Production or its popularity, or well, as I said before about the Prince and the Pauper, I guess that has to be my favorite one on the LibriVox site.
This is a relatively easy sample where the lost frames are not highly impacting the intelligibility of the speech, since the missing frames are mostly in speech pauses. Now the concealed sample.
Production or its popularity, or well, as I said before about the Prince and the Pauper, I guess that has to be my favorite one on the LibriVox site.
The concealed sample sounds a lot smoother, and quality of the audio is increased, but there is still a slight difference to the clean sample.
Production or its popularity, or well, as I said before about the Prince and the Pauper, I guess that has to be my favorite one on the LibriVox site.
Let us now come to a bit more difficult sample.
Lear hands the kingdom over to the happy couple and announces the intention of returning to a comfortable estate, accompanied by Kent and Gloucester.
The speech is still intelligible, but the quality is more degraded than in the first sample. Now let us play the concealed version.
Lear hands the kingdom over to the happy couple and announces the intention of returning to a comfortable estate, accompanied by Kent and Gloucester.
The tPLCnet manages to return a lot smoother signal, but it's not able to reconstruct the long sections since the loss is too severe, but at least it fades smoothly in and out of these sections. Now for a comparison, the clean sample.
Lear hands the kingdom over to the happy couple and announces the intention of retiring to a comfortable country estate, accompanied by Kent and Gloucester.
In the last audio sample, it is already visible from the spectrogram that the intelligibility and the quality is highly impacted. First, let us hear the corrupted version.
For more information, volunteer, please visit LibriVox.org. Recorded by Marlo Diane.
And now the concealed version.
For more information, volunteer, please visit LibriVox.org. Recorded by Marlo Diane.
The concealed signal is smoother, but the intelligibility is still highly impacted. The speech sounds generally over-smoothed and the formats are not very precise anymore. Finally, let us hear the clean sample.
For more information or to volunteer, please visit LibriVox.org. Recorded by Marlo Diane.
Since we didn't talk about the loss function yet, let us have a closer look. For the tPLCnet, we decided for a mean absolute error loss function, since it is less sensitive to outliers. In the table, we compared three different main configurations of the mean absolute error. The first one is the mean absolute error in time domain over the whole utterance, which is, since it is in time domain, phase sensitive. This loss function resulted in the lowest performance. The second configuration is the mean absolute error of the magnitude of the STFT, which has already highly improved the performance compared to the time domain loss. The last configuration is a weighted combination of the magnitude distance and the complex distance of the STFT. This approach results in the highest scores, where the PLCMOS performed best for a frame length of 32 milliseconds, and the PESC and the DNS-MOS performed best with a window length of 20 milliseconds. Because of the better performance in PLCMOS, we decided for the configuration with a combined mean absolute error with a weighting factor alpha of 0.1 and a window length in the loss function of 32 milliseconds for our final model. On this slide, the performance of the three size configurations are compared, with the zero-filling baseline and a baseline model trained on the same setup, where the context buffer is concatenated to one long feature vector and processed by 3 feed-forward layers instead of the conf1D and the BGRUs. The evaluation is performed with PESC, PLCMOS, and DNS-MOS. Higher is better for all scores. The feed-forward baseline already reaches a good quality, which is comparable to the small tPLCnet configuration. With increase of the size of the model, also the performance increases slightly for all scores. But it can be noted that the performance differences are not very large between the size configurations, which means that already with a smaller model, we can greatly improve the perceived quality. Now let us finally get to the challenge results. The largest configuration of the tPLCnet reached a robust tied third place. Interesting here is that a high PLCMOS value seems not to specifically indicate a high result in the subjective CMOS ranking. Our model reached a PLCMOS of 3.98, while the second ranked model only reached a score of 3.74, which is a significant difference. Another interesting aspect here is that even the best performing system is only able to increase the word accuracy by 3% compared to the zero-filling baseline, which could point towards that the speech recognition system can already handle lost frames relatively well, while for long losses, none of the PLC models can predict the lost information. So in conclusion, we were able to build a sequence-to-one deep PLC model, which reached a competitive third place in the first audio deep PLC challenge. The model predicts lost frames from a short context buffer and only runs when a lost frame is actually detected. The model has a straightforward architecture and is trained on a phase-sensitive mean absolute error and time frequency domain. The model was only trained on publicly available data of the PLC challenge, which resulted in a robust and reproducible overall approach. If you liked the tPLCnet and would like to know more, take a look at our conference paper or visit us at our poster. If you have any question, just contact me via email or write in the Q&A section. Thank you for your attention and for watching this presentation.